Dr. Manoj, he is Dr. Raja Selapan.
Yeah, hello.
Faculty of
Hello.
Facility. Yeah.
Nice to meet you. George, I have it.
Yes, sir. Yes, sir. Yes. Ma'am, you can start now.
Yeah. If somebody can share his bio, share screen.
1 minute.
Yes.
Yes, I may mute. Yeah, others can mute maybe. So very good morning to one and all. So we are here in the third day of our conference, first session with Dr. Manoj Gupta from NUS Singapore. So thank you, Dr. Manoj, first of all, for having accepted our invitation and honoring our session. So Dr. Manoj will be talking on magnesium-based nanocomposites for biomedical applications. It's my privilege to introduce Dr. Manoj. So Dr. Manoj was a former head of materials division of the Mechanical Engineering Department and director designate of Material Science and Engineering Initiative at NUS Singapore. In 2017, he was highlighted among the top 1% scientists of the world position by the Universal Scientific Education. His research interests include disintegrated milk deposition and hybrid microwave sintering process and energy efficient solid state processing method to synthesize alloys, micro and nanocomposites. He has published over 500 peer-reviewed journal articles and owns 2 US patents. He has co-authored 6 books published by John Wiley, Springer and MRF USA. A multiple award winner, he actively collaborates through visits with Japan, France, Saudi, Qatar, China, USA and India. So thank you once again, Dr. Manoj, and may now request you to share your screen for presentation.
Okay.
Thank you.
Thanks, Prof. Nirmala. Let me share the screen. Are you able to see now?
No, not yet.
No.
George, is it screen sharing is enabled?
Let me do it again.
Yeah.
One second. I think I'm stuck somewhere. Let me get the zoom back.
Yeah.
Share screen is here. Share. Are you able to see now?
Yes, Dr. Manoj, perfect. Yeah.
Okay.
Perfect.
Okay.
Yeah. Thank you.
Okay, a very good morning to everyone in India, and thanks to Prof. Nirmala for approaching me and providing me with this platform to talk about a very interesting topic on use of magnesium-based nanocomposites in biomedical application. Magnesium is a extremely emerging material which has not only the application in engineering but also in the biomedical at the same footing. And what you see here in this slide at the bottom are some of the applications of magnesium which are being put in the market already, like in the form of a stent, in the form of a orthopedic screws, and it's used in the human body. So human trials have started, and magnesium is also being used as a chip material for essentially controlling the blood supply post-surgical operation when they have to open the body. So in two contexts, magnesium is very important. One is in the engineering context and second is the biomedical concept. Two reasons to use magnesium. First is to control the weather, because we are seeing too many weather changes, climate changes leading to flash floods like the one you see on the left hand side that happened in Chennai itself in December 2015. Last year, we have seen the drought. So these are the extreme weather changes which never used to happen before. And in the image on the right hand side, you see the forest fire in Alberta happening at minus 10 degrees centigrade, and the France was sizzling at 45 degrees centigrade last year. So these are the temperatures in the event which we never witnessed before. The second main purpose of using magnesium is to improve the health. I'll not say improve the health of humans, but the more common is the living organisms. Now, it is our responsibility to use the right material and the right technology in the application, irrespective of the type of application. The picture that you see in this slide is one of the dog turning blue because there was a contamination in the river water, and then the chemicals released were leading to the bluish tinge on the body of the dogs there living nearby. So that is the example of bad technology used by the people. And on the picture that you see on your right hand side is of a Hulk character from the movie Avengers. Now, of course, it's a fiction movie, but at the end of the day, if the dog can turn blue because of the wrong use of the technology and the materials, we can also expect the humans also to keep changing the color. So the message in this slide is that we have to use the responsible materials and the responsible technologies. Now, why it is important? Now, the work done in CSIRO Australia have shown that, for example, if your soil bodies are contaminated, then the contaminant in the soil can go in the plants. Beside, it is affecting the living organism like animals and all this thing, but the plants can get affected as well. So what you see in the image on your left hand side is a eucalyptus leaf showing the traces of gold because the gold traces were there in the soil. And in the middle image and the image on the right hand side, you see that manganese has been gone into the plant system, transportation system, xylem and phloem, plus the leaves. So basically, what does it tell you is that you may eat healthy food like broccoli or the spinach. You can wash it for the dirt. But if this contaminant finds their way inside it, then you cannot clean it. So essentially, a choice of wrong materials or the wrong technology can lead to these materials going in your dinner plate no matter you do what, and that will adversely affect the health of humans and in general the living organisms. Now, when we say the humans and the living organism, plants are very important because the food chain, we depend on plants directly or indirectly. A clear example of that is, for example, if you look at this image on your left hand side, you will see this plant grown in a soil which is contaminated by aluminum. You can see the length of the roots is less. So if the length of the roots is less, that means the length of shoot is also less. That means the crop yield that you get per square hectare of the land will be less, and that is not a good news. And once it is there, for example, it has been also established that in the buckwheat plant, as I indicated from the research of Australia, is that even aluminum can get uniformly distributed in the leaves beside the transportation system. But for the plants to absorb this aluminum, which is one of the most widely used lightweight material in engineering application, the soil has to be acidic. Now, for the soil has to be acidic, but if you do the Google search, you'll see that 60% of the world potential crop growing land is highly acidic. So if we have to use this kind of materials which are toxic or neurotoxic in case of aluminum, we have to be very careful that we do the careful recycling. Otherwise, it will again enter in the food chain. So if aluminum do enter, aluminum is just one example. There are many elements like that which can act in a similar fashion. So aluminum, for example, since by volume it is most widely used element in the or metal in the engineering and engineering application, particularly, it can lead to the cognitive deficiency, dementia, adverse effect on central nervous system and the reproductive system. It links with the Alzheimer's disease is quite well established, and the people who are susceptible for this kind of contamination are the weaker section of the society. Similarly, what we are learning about COVID-19, that it affects the weaker section of the society and they are the one who are most susceptible. So same thing is true here. Infants, elderly people, and the patient with the side diseases like diabetes or hypertension and all this thing. And keeping this in the view, the World Health Organization is always minimizing the intake of or recommended intake of aluminum in the human body or the food chain. And essentially, this was almost 25 years back. Australia also weaned off the use of aluminum based salt to treat the water because the link was clear. Aluminum can go, get accumulated in the brain, and lead to all kind of mental health issues. Now, what happens if we use magnesium is magnesium is a nutritional element. After calcium, which we need about 650 mg per day, you need calcium up to 420 mg per day, depending on the age, your age and sex and maybe some other factors. So if magnesium contaminates the soil bodies or the water bodies, for example, you see that the plant on your right hand side is having longer root length, and longer root length, if you talk with the botanists, translate to the better shoot length also and the better size and quality of the plant. So essentially, magnesium is a non-toxic material and it is used for the human body for many reasons. Like it is involved in the 300 chemical reaction in the body. It is required by the muscular system, nervous system, cardiovascular system, immunity system. And of course, if you have trouble sleeping or hearing loss, you can also use magnesium as a medication. And no doubt, and it is no wonder that magnesium is the fourth most abundant cation in the human body. Now, let's go into the use of magnesium in the human body, because we have learned that it is a non-toxic element, so it can be uh, uh, very well used within the body without giving any systemic uh, toxicity. So you see that in the body we use metal-based implants in many areas. There are two type of implants: permanent implants and non-permanent implants, which you can call as temporary implants. Permanent implants refers to, like for example, the implant of the hip or implant of the knee. So these you want to stay in the body. You don't want it to happen anything to them. But for the temporary implant, they have to be put in the body till the your healing is finished, and then you don't need it. So normally people go for a revision surgery. They once the wound is healed or the bone is healed or the crack is healed, they have to take the steel nails, for example, out of the body, because normally they use steel nails. It is very cheap, but it's quite bio inert in a way, so it has to be taken out, otherwise it lead to a lot of discomfort in the body. But if you use the magnesium implants with the right properties and the right degradation, then in that situation, this element can dissolve in the body once the wound is healed up. Now, that is one of the reasons why magnesium is emerging as a biomaterial. Almost for last 10 to 15 years, there's a lot of research going on. I think the Germany is doing a good job in that. And they have positioned themselves very well. And you can see the cardiovascular stent made of magnesium in the top picture, and the compression screws, what you see in the bottom image, are already being produced and available in the market at a very high premium. So why we use this one? Because when these people sell this implant, so you can learn from how they are selling it. You see that they are stable, they are stronger, they are osteoconductive. You don't need to remove them. So you avoid the revision surgery and the patient costs and the trauma. It can help in the remodeling of the bone. And then its biomechanical properties are closer to bone. It avoids stress shielding, anti-infective, no known allergy, and you can track it using MRI or CT scans actually. Now, looking into this kind of progress, now South Korea is also doing very well in developing this kind of thing. Japan is coming up, especially in designing the clips to stop the blood flow post surgical operations. So where is magnesium? If you know the periodic table, I'm sure most of you know about it. You see that magnesium is the group 2A element. It has certain positive points. It has low melting point, low density, high specific strength, good damping, electromagnetic shielding, and it has acceptable ductility. Modulus is very good. When you talk of the biomedical application, cost is very reasonable, much cheaper than titanium. And only problem it has, which people try to fight it out, is its degradation aspects in the when it is exposed to the wet environment. So let's try to compare with three main elements: aluminum, titanium, and steels. Of course, out of these three elements, titanium and steels are the one which are used as a biomaterial. So if you look at this graph on your left hand side, you see that magnesium is the lightest. It has a lowest melting point. It has a similar specific modulus even to the titanium, and its specific strength is only next to the titanium. So in a way, it is better, holistically speaking, is even better than titanium when it comes to the temporary implant application. I'm not talking of permanent implant application. So why these characteristics are important? Because it needs low energy for melting. It can be cast very well. It can be machined very fast and all these things. So if a material can be converted into a product very fast, it's very important for bringing it cost down. If your material is very difficult and high temperature melting point and all this thing, it increases the cost of the implant. So from that perspective, magnesium is perhaps one of the best, even when you compare with titanium and steel, and of course the other medical benefits. So the next thing which people see for a material to be introduced into the market is that it's not in the short supply. If you're in the short supply, the cost goes up, and we depend uh, on the countries which is supplying this material. And I think some of you may be aware how difficult it is to get the magnesium powder in India when you want to buy from the overseas resources. I have personally seen that kind of issues. So yes, we are not short of magnesium. It is sixth most abundant element in the earth crust and third most abundant element in the seawater. Uh, in terms of its elemental abundance, it is almost 12 times more of aluminum, and it is next to iron. So in a way, it can really last for a very, very long time. So it is in abundant supply, not only on the planet Earth, but in the whole universe. It is much more than uh, iron. So it is most available metallic element, I will say, available in the whole universe. And the recent investigation, for example, below the Martian surface have found a lake. And what do they found in the lake? Magnesium, calcium, sodium. Now, magnesium, our body needs. Calcium, our body needs. Sodium is an electrolyte. We need it. So basically, you see that how what we need is also available on the planets in a way. So that is why I say that magnesium is the God's own element. It is widely available in the whole universe that we live in. So what are the key issues of using magnesium-based material as a temporary implant? We have to be careful about the composition. We have to add the element that does not create local or systemic toxicity. We have to be ensured that these materials can be processed which are scalable and industrially adaptable. We can do the work in the lab, but at the end of the day, if it has to see the light and it has to reach the access of a common man, the processing technique should be scalable and should not be very expensive. It should have a acceptable mechanical properties, because when you use as an implant, it has to have good mechanical properties. And of course, it should have good corrosion and degradation response, which can be tailored based on the healing response of the typical injury that we are handling with. Now, if you look from a different perspective, there are a lot of degradation benefits of magnesium. There are four things that you can expect when a magnesium degrades. The first is in the increase in the magnesium ion concentration. In, but when you increase the magnesium ion concentration, if you look at this one slide, it increases the bone cell activation, promotes bone growth. It also leads to the increase in the pH because OH minus ions are released. But once that pH is increasing, it also increases the oxygen pickup by hemoglobin, and it minimizes the bone desorption. Hydrogen bubble formation, hydrogen is an antioxidant, it reduces the cytotoxic oxygen radical and so on. And the formation of apatite layer, CAP layer. And but the formation of that increases the osteoconductivity, and it assists in cell attachment and the tissue growth. Having said good points here, it has to be ensure that the degradation is controlled. If all this thing happened too fast, again, it's not a good news. If it happened too slow, again, it's not a good news, because we lose the purpose of putting temporary implant which dissolve in the body. So we have to control this degradation so that this become beneficial for the patient who is using it. Now, the focus of my talk is on magnesium nanocomposite. And so I have to tell that if you use the reinforcement judiciously, I'll say the word judiciously, then you can improve the microstructural characteristics, you can improve the properties of the material. And once the property goes up, the performance of the material goes up, whether it's a metal or alloy. So let's try to have a look at magnesium nanocomposites. What is a nanocomposite? A nanocomposite in which one of the microstructural features in the nano length scale. That's how we call it as a nanocomposite. The picture on your left hand side, you'll see that there's a big particle in the micron length scale. We called it as a microcomposite. But the picture on your right hand side, you see the Al2O3 particles are in the nano length scale. When I say nano length scale, that means the size less than 100 nanometer, we call it a nanocomposite. But this size length scale of the reinforcement makes a tremendous difference in the properties of magnesium. So we use a nano reinforcement because it has a capability to improve the strength and ductility. It can improve the wear resistance. It can improve the fatigue performance in the dry and wet corrosion resistance. These first four properties are very important for the bioapplication. And for engineering application, you can add these four properties to the below properties like dynamic properties, modulus, high temperature, stability, creep performance, and the ignition performance. So when we use the nanoparticles or the particles in the nano length scale zone, it avoids two things. The picture on the left hand side, you will see the particles are breaking. This happens when you have the micron size particles and higher sizes, or they debond. So once these two damage mechanisms comes in, then what happens is that you do not realize the strength and the ductility and the toughness of the material. The ductility can be compromised almost by almost 80%, and which is not a good news. So essentially, that is the main rationale of using the nano reinforcement. So in this work, we have chosen different alloying element and in the level which is not toxic for the human body. Some of the elements which we have investigated is diosporium, zirconium, manganese, gadolinium, and zinc. And what you see on this thing is a safe limit of these elements in the human body as an alloying element, not as a base element, only as an alloying element. And we have tried different type of reinforcement, and some of the reinforcements are titanium based, like pure titanium, titanium dioxide, carbide, titanium nitride, and titanium diboride, hydroxyapatite, and silicon dioxide. We make this material in our lab, and we use the two techniques because there are two techniques which are generally used to process any metal-based materials or composite. These are the liquid-based methods and the powder-based methods. In the liquid-based method, we innovated way back in 1995, which is almost 25 years from now. And this is called as a disintegrated metal deposition technique, in which we just take the material in the crucible and we heat it up to a 750 degrees centigrade. We homogenize for temperature and particle reinforcement. We bottom pour it, hit with argon gas jets, and we get an ingot. And it's a very, it's a technique which is not cost intensive, and it can be like fabricated at a very low cost. So you can get ingot and you can machine it. Now, just these facilities which can melt up to 750 gram of magnesium alloy in one time, and you can run this twice in a day, it can cover about 10,000 surgeries. It can cover 10,000 surgeries in a year. So you see that how much we can cover just with a lab scale model here. And the similar capabilities you can do with the powder metallurgy, even at the lab scale. Powder metallurgy is an established technique also, and in that you mix some powder with the reinforcement, you blend it, compact it, and you sinter it. We opted for the microwave sintering because it's an energy saving technique. The microwave that you use is the one you use in the home. 900 watt or 1 kilowatt is good enough for that. And let me explain you how it works here. You take a microwave, you take your billet, it is about 35 mm in diameter, 1.5 inch roughly, and about 40 mm in height. And it is placed in an inner crucible. Then you have a silicon carbide susceptor. Then you have an outside crucible, and then you have the reinforcement, that insulation to confine the temperature into this setup. So we calibrated the microwave for the temperature we need. And for example, we can reach 640 degrees centigrade in just 14 minutes, 1-4. So switch on for 14 minutes and then it gets switched off and your sintering is done. And you save 91% of the time here. And as I indicated before, if you can do a thing faster, your product output is faster, your cost of the product is lesser. Then you go for the energy, fossil fuel consumption. Remember the global warming and everything? You can save 90% and beyond when you use this kind of sintering. So that is why this is one of the most uh, researched area, and there are a lot of companies who are trying to bring the microwave furnaces now in the market at the industrial level. So when you have the microwave, this small animation shows that how the microwave comes in and heats the billet from inside to outside and outside to inside. And you get a very uniform temperature distribution, which lead to a very good microstructural uniformity. And this slide shows the specification of the oven, which is a household oven, and the billet you can extrude it, no problem. And you get the properties similar or better than conventional sintering as per our work done quite some time back now. Now, once you use the right material, once you use the right processing, then you have to characterize it to ensure that it really behaves in a way based on what is governed by the end application. So let's try to have a look of some of the magnesium-based nanocomposites which we worked on using elemental titanium and titanium-based ceramics. Why we use elemental titanium powder? Because it does not react with magnesium and it improves the performance of biomechanical performance of magnesium. So since we are putting in the nano size, so you see in this table, all the amount of the reinforcement that you put in the magnesium is typically almost like not exceeding 3 weight% of the reinforcement. Look at the UTS value. The UTS value are typically higher than the strength of the bone, which is 149 megapascal. The fracture strain is again much higher than the tensile ductility of the bone. So we are actually so these material in a way are stronger and tougher than bone. So from mechanical perspective, they qualify. And when we look at the compression properties, once again, you see that the compressive properties are again much higher than what is the compressive strength of bone at 167 megapascal. Then we did the corrosion test on in physiological medium, DMEM plus 10% FPS, and the corrosion result shows a very low corrosion rate at 0.1 millimeter per year, less than that. So that means this number, when you talk with the surgeon and you compute the healing time of the bone and cracks and all this thing, you see that they need something less than 0.2 mm per year. So these materials do qualify from the corrosion point of view also. When you do the corrosion testing in the physiological medium, the pH changes. When the pH change is high, that means your corrosion is high. So when you choose a reinforcement, for example, it's not like you choose any reinforcement, you have to choose the best reinforcement. Now, in this graph, for example, you see magnesium TiO2 in the top left-hand corner. And you see that at 2.5% for 50 days, the pH fluctuation is very less. So if I have to go for MgTiO2 system, I'll go with 2.5% TiO2. On the other hand, for various reasons, if I want to take TIC, then I will go for 2% of TIC in my matrix. And you see the pH is very stable, very, very stable for all the volume fraction of TIC. And if I have to go for TIN, again, any amount up to 2% is okay with me, because again, the pH fluctuation is very limited and that's what I want to see in the body, not too much pH fluctuation. So the message from here is that every system has its own characteristics. So you choose which amount of reinforcement you want by looking at the mechanical properties and the corrosion properties. Don't add too much. If your 0.5% of TIN can do the job, why you want to go for 2% of TIN? Go for zero point 0.5 only. So we are doing some work with dental surgeons in National University Hospital here, in collaboration with the PhD student Soma and Professor Raymond Wong for mandibular reconstruction. And in this situation, we use a magnesium and we investigated nanosilica particles and the nanohydroxyapatite particle as a reinforcement. We use a photometallurgy method just to have a fair comparison between the silica and hydroxyapatite. And we put this material for hot extrusion and we try 0.51 and 1.5 volume percentage of reinforcement. What you see in this picture is quite a uniform distribution of the hydroxyapatite particles here, which was confirmed by the EDS analysis. That shows that our processing technique is good to give a uniform distribution. Note that uniform distribution, we want to have uniform properties and uniform corrosion response. And this slide shows a similar result for nano SiO2 particles. SiO2 is also very biocompatible. At times it is also called as bioglass. Then we look at the tensile properties, and you see that how the properties changes with the amount of reinforcement. And we see that the best properties are exhibited by 1.5 SiO2, and even 1 SiO2 gives a wonderful ductility and acceptable UTS and very good absorption of the energy under loading. And of course, we also see that how the fracture behavior changes when you put these particles, and we see that there's not much difference in the fracture response. So it will not adversely affect the properties of the base magnesium. Then these in vitro studies were done in collaboration with Professor Wong and Soma, and they used the MC3T3E1 pre-osteoblast cell. They did the cell proliferation assays, cytotoxicity, live and dead cell staining, and the cell attachment, which are the standard tests which people do to assess the compatibility of the material. So in the MTS assay done on magnesium nanohydroxyapatite composite, they say that all the composition, if you see this one here, all composition were non-toxic because the cell viability is beyond 75% in all the cases. So that was a good news. And then we also look for the cell survival studies, and you can see the blue numbers in this table are the one which shows no cytotoxicity, and the green one is the mild cytotoxicity and the red one are the moderate cytotoxicity. So obviously you want to go for no cytotoxicity or mild cytotoxicity. So that way magnesium 0.5% HA and magnesium 1 hydroxyapatite are the one which you should further focus on. Similarly, when you look for SiO2 reinforcement and its effect, once again you can see that it is working better than hydroxyapatite, which was a bit surprising for us, but not too much surprising. And magnesium 0.5 is totally not cytotoxic. Magnesium 1 SiO2 only on day number 5 is 79%, which is almost close to the zero cytotoxicity, and magnesium 1.5 for one day was okay, but then it enters into the severe cytotoxicity zone. So once again, 0.5 and 1% SiO2 are the potential material for the future consideration. We also try to understand cytotoxicity percentage from the lactate dehydrogenase enzyme release assay, because that is, they don't do one kind of test. They want to do a few tests to understand what is the holistic response of the material. And so that is a norm by the doctors in general. So essentially, once again, from LDH release, they say level 0 cytotoxicity if the release is less than 25%. If it is between 25 and 50%, they say level 1 cytotoxicity, and level 2 is 50 to 100%, and severe cytotoxicity at 100%. So basically, you want to go for 0, but 1 is acceptable at the lower numbers like 25 to 30%, so on. These are the details of how they did it. And when you look at the hydroxyapatite containing magnesium composite, you see that all the compositions almost show the zero cytotoxicity except for magnesium 1.5 HAP, which is almost like 35%, 36% here. So most of the results are good, but if you want to play safe, go for again 0.5 and 1% HA reinforcement. And if you look at nano SiO2, it works better. Now, in this situation, all of the composition up to 1.5 SiO2 has a better performance in terms of LDH release results. Then we also did the live and dead cell stainings, and I will show you some pictures here which are taken at day 1. Just look at the last column where we merge everything, live cell, dead cells, and the nucleus of live cells, and you see that all the samples reasonably show the presence of the live cells. Again, we use MC3T3 even pre-osteoblast cell line. You can see all composition are showing the uh, very good presence of the live cells, and this is a day 5 for nanohydroxyapatite. So apparently, once again, the best density was for 0.5 HA and the 1 HA. But nevertheless, 1.5 HA, if you look at the bottom picture, is also very reasonable. But when you compare it, 0.5 and 1 are the best. For nano SiO2 done under the same condition showed the similar results also. As you can see in the picture, keep focusing on the column on your right hand side. Now, we also, so what do we learn from this live and dead cell staining is that for both the composition like nanohydroxyapatite and nano SiO2, we found very few dead cells. And based on all the results and observation and the quantitative analysis, we found that 0.5 and 1% nano SiO2 and nano HO, both of them in the same amount are showing the best results in terms of the cell proliferation and cell uh, uh, non-toxicity and cell not dying and so on and so forth. We also have to see that how the cell attach to this material, because once they are used as an implant material, they have to attach to the surface. And for both the material, again, we did not find any difference. And if you look at the picture on your right hand side, day 7, all these flat cells are very nicely attached to the substrate of these materials. We also did the immersion corrosion testing in the Hank solution. And if you look at the composites with nano hydroxyapatite, you see it is quite 0.8, 0.9, and for Mg 1.5 H is 1. So if you look at this number, they're not too different, but they are increasing with an increase in the amount of reinforcement. And the second way to look at it is that all this corrosion rate due to the presence of HA is much lower than the pure magnesium. So it is a beneficial effect of the nano reinforcement to improve the corrosion response of this material. And to note that actually, if you do the same test in vivo, the results have shown that actual rate of corrosion is almost 1/4 or 1/5 of what you see in the in vitro situation. So these are all acceptable material from that perspective. If you look at the graph, all these 3 composite materials are way superior than the pure magnesium. Now, if you look at the pH values, again, similar to the corrosion rate, you will again see that pH values are quite similar to them, but the best values are still, if you really want to compare, is for 0.5 HA and the 1 HA thing. And we also look at the optical microscope to see that it is more of academic interest that if the corrosion takes place, how it takes place. And like other studies done by other researchers, we found that the pitting corrosion is the main form of corrosion which affects the degradation of this material, whether it's nano HA or nano SiO2 material. For SiO2, again, we have seen the rate of corrosion was marginally higher than HA, but typically better than the pure magnesium. And once again, these materials also shows the pitting corrosion as the main form of corrosion which degrades the layer, the protective layer, and affects the corrosion of magnesium. So all these results, how do we summarize these results? First is the effect of amount of silicon dioxide and hydroxyapatite reinforcement, and we found that the both of the reinforcement in the same amount lead to the better cell proliferation and the corrosion response. Now, if you compare between which one is good, SiO2 or HA, then we have seen that SiO2 reinforced composites have shown better cell proliferation, and then they also have shown less cytotoxicity percentage. So if you have to really choose, I will say that SiO2 overall have an advantage over hydroxyapatite, unlike the conventional belief that HA will work better because it's closer to the bone and all this thing. If you look at the immersion response, HA composites have marginal advantage of SiO2. But when you choose a material or a composite of anything, you have to look at the holistic uh, properties in one snapshot, and in that I think MgSiO2 system is have a slight edge over MgHA system. So what we do now, it's a typical thing which is used by the companies to qualify a material for uh, human application, is that you try to develop a new material, then you do the mechanical testing on that, then you see the in vitro degradation, you go the cytotoxicity, osteogenic effect. So we have done all this thing. We have the only thing for this material now, the next step is the in vivo evolution in the small animals like rat, guinea pigs, and take it to the big animal like sheep or monkey. Now, what we are doing now is that pure magnesium is, of course, it has given the promising result, but that is not the end of the day. We have to keep looking for new systems which can be even better. So we are trying to develop new binary and ternary alloys for standalone, like they can be used on its own or in the form of composite. But at the same time, we do not want to add too much alloying element. So we go for the concept of micro alloying. That means typically less than 1% of the element. So make it as simple as possible. So we tried element like zirconium, manganese, and dysprosium in that. And you can see that by putting this element, of course, your strength level, it may not be as good as your magnesium, but it is always superior to that of the bone. So we need the strength levels to be superior to the bone. We need the reasonable ductility level beyond 2%, so which happens in here. And now, if you look at the rate of the corrosion, because once the mechanical properties are qualified, then we have to look at the how do they uh, corrode in a wet environment. So by looking at, it's only like putting zero point 0.5 zirconium, zero point 0.5 manganese, and zero point 0.5 dysprosium, you see that zero point 0.5 dysprosium, just only 0.5, can give you 0.29618 millimeter per year of the rate of corrosion. And manganese is also equally good because remember, in vivo, you have to divide it by 4 or 5. So these two systems seems promise. So now you have to develop it further. So we put zinc. Zinc is again a biocompatible element. And now we do the systematic studies of seeing how the 2.5 zinc is, how the 0.5 dysprosium is, and how is, when we combine both of them, how do they work out? Microstructure is good with only 5 micron grain size, much better than the other two composition. And if you look at the thing, you see the yield strength is high, than 2.5 zinc, similar to dysprosium alloy. And if you look at the UCS, it goes up. But anyway, all these properties are superior to that of bone. And we have a wonderful ductility. So this material is very, very tough. So we are okay from the mechanical properties. We also look at the vibration, because the vibration can lead to the fretting damage, and also it can lead to the, because our implants are subjected to the cyclic loading, and fretting damage can lead to the cyclic failure. So we also look at that. So this alloy has marginally higher damping response or to kill the vibration. And then we did the immersion characteristics in the hang balance solid solution, and you see that magnesium with 2.5 zinc and 0.5 dysprosium has a very low rate of corrosion. So now we have improved on the mechanical properties and we have improved on the immersion characteristics of this material, which is very good. And this graph shows you, the red curve shows that how much is the corrosion rate immediately goes down once they're exposed to the solution for magnesium 2.5, 0.5 zirconium, and the pH fluctuation are less when compared to the magnesium with 2.5 zinc. So how do we compare with the other research alloys? You see that it's almost an order of magnitude better in terms of the rate of corrosion. So this is a system which will pursue further to make composites or do the uh, more detailed in vitro and the in vivo studies. So that's how we go. So in conclusion, I would like to say that there's a tremendous scope of magnesium technology in the biomedical application. If you ask me how big is the world market, I will say about 10 to 12 billion dollar. And this market is almost untapped. There is players coming in. Germany is coming in, South Korea is coming in, and Japan is coming in, but no one is yet there, and no one has a strong foothold. So it's the right time for the people or entrepreneurs to come in from practically any country. You put up a good product, it will sell. And a lot of people who are willing to buy this product was much cheaper than titanium. The second thing, which is very important from the industry point of view, is that we can use the conventional methods. We don't have to invest a lot of money. You can easily buy the very simple furnaces and all this thing and do the needful. Number three, if you want to go in the composite technology, don't go for the micron size particles, go for the nano size particle. Because just by putting a very small amount, if you put micron size, you have to put 20%, 30%. If you put nanoparticles, you're only putting like not more than 3 weight%. And the best results, for example, the one I have shown to you, comes around 0.5 and 1% volume percentage, which translate to maximum of 2.5% by weight, depending on the type of reinforcement. And they can do the amazing job in improving the properties of magnesium. We are also trying the hollow SiO2 particles also because they are even better, and it can make your implant even lighter. So in a nutshell, my message is this: magnesium technology has arrived and it is time for industry and uh, uh, doctors to adopt it. And doctors are having open mind, because when I talk with some doctors here, we have a lot of interest in Singapore. Recently I talked with some doctors in India also. They also have a very strong interest to work with us on this technology. So my recommendation is that if you are in this technology, please go ahead and create your own foothold. And India is a big market, for example. ASEAN is a very big market. And you have Africa, you have Middle East. So if you look at your neighborhood, for example, there's a lot of scope to move on that. And with that, I conclude my talk. And thank you very much for being here and for listening to my talk. Thank you.
Thank you, Dr. Manoj Gupta. It was indeed a interesting lecture. The participants have posted a lot of questions, so I'll pick few questions to you.
Okay.
Yeah. How long does magnesium nanocomposite last in the body?
Okay, that is the in vivo thing actually. It depends. You can tailor it. Now, you typically, depending on the age and sex and the intensity of the injury, you need implants maybe from a week to maybe about 3 months time. So you, depending on what composition you're talking, you can tailor the degradation based on the healing time. So there's not like one size fits all. You have to tailor your material. For example, we are trying to go into the cranial thing, and in that we are trying to first target where the healing time is fast. So it all depends. Remember that many of these materials are still in vitro stage, and we still have to do some work in the in vivo. So I cannot really answer that thing, but if it can last, for example, as an example, in 1 week in vitro, so divide by, so multiply that by almost 4 times, so it can easily stay for 1 or 2 months time in the body, the one which we are investigating.
Thank you, Dr. Manoj. The other question is, can you throw some light on Magnesium and combination of cobalt compounds.
Don't use cobalt and chromium because cobalt and chromium both are toxic elements. Okay, if you recall, there is a lawsuits filed on DPI, which was a subsidiary of Johnson and Johnson, when they put cobalt chromium as a hip implant, and they can corrode, they can lead to the local toxicity. When these patients were diagnosed, their levels of cobalt and chromium, which are both toxic elements, were 10 times higher than that. It destroys your muscles. I will not say it is a solution. And moreover, cobalt chromium was more targeted as a permanent implant, not as a temporary implant. Okay, so my personal view is that do not use cobalt chromium in the body.
So, it's another question from Dr. Manimori. For pellet preparation, which method is giving high density, hot press sintering or spark plasma sintering?
Spark plasma sintering and hot processing, I will say the main limitation of the spark plasma sintering, beside its unique advantage, is that what is the size of specimen you can compact and sinter at one point of time.
Yeah.
So you have to ask yourself a question. You may get good results, but at the end of the day, can you scale it up? If you cannot scale it up, then it is only of the academic interest.
Thank you. So, one last question. Can we use biocompatible anti-corrosive coating of magnesium implants for permanent implant applications?
No, I will not say that. Uh, Magnesium is electrochemically active when compared to titanium and steel. So basically, if your main objective is a permanent implant, you should not be using magnesium. Absolutely not. Why? Because the coating has a life. Once the coating is damaged, your magnesium will start to corrode. And you don't want your hip implant or the knee implant to corrode, because once you put it in, you give it a life of about 10 to 20 years in there. You do not want intervention. These are the big surgeries. So magnesium is targeted only for the temporary implant application.
Yeah. So I think we'll stop the session here for want of time, though there are many questions. So thank you once again, Dr. Manoj Gupta, for
No
giving
problem.
such a wonderful lecture. And on behalf of our center and BAT, thank you once again for joining your conference.
Yeah.
Yeah, thank
Pleasure.
you.
Pleasure.
Yeah,
Thank you,
pleasure.
everyone. Yeah.
Yeah,
Yeah.
thank you. Thank you.
Yeah. Okay. Bye.
So we'll leave the session and join back for the next session by Dr. Prashant.